Hi guys, it's Kate, and this is the first video for week 10 of Math 23B. Let's begin. Alright, so we basically need to figure out how to compute various integrals over manifolds, and knowing that part of that involves putting everything in terms of a parameterization, it does matter whether our parameterization is orientation preserving or orientation reversing. Even something as little as the order in which we name our parameters can change the answer we get when we integrate various forms over a particular manifold. So let's take a look. We say that a parameterization T of V maps the k-standard basis vectors in parameter space into a basis for V. And if this basis is a direct basis, perhaps as tested by a k-form, or maybe just saying that is a direct basis, then T is called orientation preserving. Otherwise, it's orientation reversing. We can also parameterize manifolds by using relaxed parameterizations, the same kind of standards we'd use if we were calculating volume with them. And what we end up doing is taking a subset of Rk, that's U, right here we've named it. It's an open set whose boundary has k-dimensional volume 0, and we choose a parameterization that takes us from U and maps us onto the manifold, right? That is what a parameterization does. And we know all the basic rules about how that works. Now, for any point that's in this parameter space, but not on the boundary of it, like, an interior point in there, the columns of the Jacobian matrix of the parameterization, gamma, they're going to form a basis for the tangent space to the manifold. This is something that you already know. You used it last week as well. The parameterization is going to be called orientation preserving if, for all of the points in the interior here, right, the parameter space, but not without its boundary, if those columns of the Jacobian form a direct basis for every single value that the parameters can take on over the entire interior of the parameter space for this manifold. Now, if this manifold was originally specified by a parameterization, and it meets all the requirements of a manifold, then it's usually just simplest to specify the orientation of the manifold by saying this parameterization is orientation preserving. It really depends on the situation. Sometimes you're given a locus function first, and then you have to come up with a parameterization and say whether the parameterization is orientation preserving. Sometimes you're given a parameterization that describes the manifold. Remember, there are 3 different ways. You could do the graph of a function, you could do a locus function, you could do a parameterization. All of those are valid ways to describe a manifold. But if you're coming up with a parameterization, you want to say the parameterization is orientation preserving if, for all the points in parameter space except for the boundary, the basis for the tangent space gives a direct basis. One of the main theorems about this topic in Hubbard says that as long as we use only orientation preserving parameterizations, integrating a form over an oriented manifold is going to be independent of choice of your parameterization. So if we switch to an orientation reversing parameterization, though, the sign of the integral will change. The magnitude will stay the same. So if we integrate a k form over an oriented manifold, we're free to use any convenient parameterization, but you do need to keep an eye out for whether it is an orientation preserving or orientation reversing parameterization. And we'll be doing quite a few examples in class this week. Moving on, it's important to touch on form fields on R3 because they have important physical properties that come up in physics all the time. So let's take a look. Right off the bat, any zero form field its integral over an oriented zero-dimensional manifold is its value there, whose sign depends on orientation. Now, a one-form field can be identified with a vector field as a work form, and the integral over an oriented one-dimensional manifold, like a curve, corresponds to the work done by a vector field to move a particle from the start of the curve as defined by your parameterization to the end of the curve as defined by your parameterization. A two-form can be identified with a vector field as a flux form. The integral over an oriented two-dimensional manifold, a surface, so you integrate flux forms over a surface, it's going to correspond to the flux of the vector field through that surface. So especially if the vector field has a physical meaning to it, like fluid flow or airflow or charge, that happens as well. But what you'll be computing is flow through the surface. And last but not least, a 3 form is the mass form of a function like charge density or mass density. It is of the form dx wedge dy wedge dz, and the integral over an oriented three-dimensional manifold corresponds to the total amount of charge or mass that's contained in the subset of R3 that you're looking at. We'll be doing quite a few examples in class, just working on parameterizing the manifold and then computing these various integrals of these 1 forms or 2 forms or 3 forms over the various dimensional manifolds, and then talking a little bit about what the significance of these results that we're getting, the numbers that these integrals evaluate to, at the end. Now, what we're building up to as we're talking about these differential forms is an understanding of this theorem, which is called Stokes' theorem. It's a major theorem in calculus, and there are a couple symbols here that you don't yet know, but that's okay. We're going to move through them. And part of our discussion right now is specifically on this guy right down here. Now, the manifold's name is X. Well, the manifold's name is M, but the piece of the manifold that we're integrating over is X. So what this is saying is that there's an equality here. You have some options. You can either integrate this guy, which you guys don't know yet, over X, or you can integrate phi, which is a K form, over, well, this looks like a partial derivative dx. Well, what this notation means is the boundary of x. That was sort of a really long time ago in maybe September or October when we first discussed that, but that is the boundary of x. And so the fact that you have this option, you can either integrate phi over a boundary or d phi over the piece of the manifold, that means that just like you needed orientation for the piece of the manifold, you also need orientation for the boundary of the manifold if you're opting to compute the left-hand side of this equation rather than the right. So while the right-hand side's integral only depends on the orientation of M, the left-hand side's integral depends on the orientation of the boundary, and the fact that this equality needs to hold means that the orientation of both x as well as x's boundary, they need to match. Their orientation needs to be consistent in order for you to get the same thing on either side. So let's talk about the orientation of the boundary of a region. We'll get to that weird bold D later. So let's talk about a K-parallelogram first of all. This is our notation for a K-parallelogram. It's anchored at the point X and it's spanned by V1 through Vk. And the order of the vectors matters. If you swap any pair of them, you're going to reverse the orientation. And so what's interesting to note is that the boundary consists of K pairs of oriented K-1 parallelograms. And you can think of that in a concrete example and you can think of that in the three-dimensional case with a parallelepiped. Here's one. I'd tell you that that was a sound effect, but that was actually my cat Max. He's really apparently not into K-parallelograms. But anyway, as we're taking a look at this, we can see that this 3-parallelogram is created by 3 pairs of 2 parallelograms. They make the faces of this parallelepiped. I've highlighted one pair just for sake of illustrating. And so the 2 parallelograms in each pair have different anchor points and opposite orientations. One of the anchor points is anchored at x, and one of the anchor points is anchored at x plus one of the vectors that spans the parallelogram. What's interesting is that we end up with these pairs by omitting one of the k vectors. And when the index number on the vector that you've omitted is odd, the remaining vectors form a direct basis for the face anchored at x plus vi, right? That would have been this back face, this back-facing one here. But they form an indirect basis for the face anchored at x. And when I is even, that rule is reversed. So that's very important, and it really depends on how you've numbered the various vectors in that K-parallelogram and so on. And don't feel too overwhelmed by that. We are one of your proofs for this week. In fact, I believe it's the first proof of the week is going to be based off of this fact, and you will go through an example and really work through it in class. This builds up to the general rule for orienting part of the boundary of a piece of a manifold. So when you're at a smooth point on the boundary of this piece, you choose a direct basis for the tangent space where the first basis vector points out, and all the other k-1 basis vectors are tangent to the boundary of P. These other k-1 basis vectors are then a direct basis for the tangent space to the boundary of that manifold at that point. Here's the same statement, but just said specifically in terms of form fields. You have a k-form that orients the manifold. You need a k-1 form that orients the boundary. So just choose any vector that is in the tangent space of the manifold but points out of the boundary. Then the k-1 form, computed in the typical way, orients the boundary. This is going to be a multilinear function of its last k-1 arguments. Now, a special case of this rule of thumb is used in physics. It's called the right-hand rule, right? You orient your right hand so that it is inside P and the thumb points out of the sphere, and then the fingers end up making a right-hand circle around the boundary in the direction of their orientation. We use this all the time, but that is exactly analogous to what we're computing here. It's just that ours works in k dimensions rather than, well, just the limited dimensions that your hand exists in are 3. We've talked about orienting the boundary. The other symbol that you were unfamiliar with in that Stokes theorem moment on the previous page was that big bold D, and that's called the exterior derivative. And we're going to talk about it, its definition, and how to compute it this week in class. So consider a one parallelogram in R that's just a line segment. It's anchored at X. Its one and only side length is H. So it's just the oriented segment from X to X plus H. And the oriented boundary of this segment consists of 2 points. The point X plus H has a positive orientation, while the point X has a negative orientation. And the integral of a zero form, a function f over the entire boundary, is as follows. It is the evaluation at the endpoint minus the evaluation at the beginning point. Note that we are specifically integrating over the boundary. So that's what that means. This is not a typical integral where you're integrating over the entire segment. This just means we're integrating over the boundary of that. Now, Stokes' theorem states that in general, the integral of a form field over the boundary of a region is going to be integral to the derivative of that form field over the region itself. And in this simple case where the region is the oriented segment, x to x plus h, and the form field is the function f, it basically states that these two things are equal. On the left, we have a zero form, the function, integrated over the boundary, right? We just have the endpoint minus the beginning point because of their opposite orientation, or we have the option to integrate the derivative of that function over the entire region. And this looks very familiar to you. This is the fundamental theorem of calculus. And Stokes' theorem is a broader generalization of the fundamental theorem, and that's why it's so powerful and so important. Note that if that derivative here is continuous, you can divide by h and take the limit as h goes to 0 to get the formula for the derivative right there, tying in familiar properties that you've already been introduced to for probably more than 2 years now in your study of calculus. Now the question is, of course, how does this generalize into higher dimensions? And this is when it's really important to figure out how we handle the exterior derivative of a k-form. So given a k-form phi, we define the exterior derivative d phi by generalizing this following rule. The derivative d phi is a k plus 1 form, so it is an alternating multilinear function of the k plus 1 vectors that span the k plus 1 parallelogram anchored at x, and it's defined by the process of integrating phi over the boundary of a scaled down version of the parallelogram, dividing by the factor that scales the volume of the parallelogram and taking the limit as the scaling factor h goes to 0. The same thing is happening on a simpler scale up here when we're looking at the limit definition of the derivative. So right here, this is Hubbard definition 6.7.1. This is what is the exterior derivative of phi, which acts on a parallelogram anchored at x and spanned by k plus 1 derivatives, and it's going to be the limit as h approaches 0 of 1 over h to the k plus 1th power. And here we are taking the integral of phi itself and integrating it over the boundary of this k plus 1 parallelogram anchored at x. Now this can get really tedious because you already saw that with a 3 parallelogram you have 3 pairs of 2 parallelograms, and that would mean that you would need to integrate phi over each of those faces, all 6 of them. But luckily, the examples that we'll be doing in class will not be too crazy. We'll usually just be doing 2 parallelograms, in which case the boundary is 4 1 parallelograms. So we'll be taking it nice and slow. We'll be doing a lot of in-depth examples. We'll be talking about how to compute the exterior derivative from the definition, just like when you were first introduced to the limit definition of the derivative and you were asked to take a bunch of limits at first. And then, of course, as you may have guessed, just as there are derivative shortcuts, there are exterior derivative shortcuts as well, but we will get to those in due time, I promise. But you can see quite a few similarities between our notion of the derivative and the notion of the exterior derivative. Now, this definition gives the value of the exterior derivative evaluated on a specific sequence of spanning vectors v1 through vk plus 1. And since the exterior derivative is multilinear and alternating, all you really need to know is its values on sets of basis vectors where the indices are in order, and then you can reason out the rest. This bottom note is basically what I just said, that integrating over the boundary of a parallelogram frequently involves a lot of integrals. We will learn some shortcuts in due time. Let's talk about them right now. Again, you'll get a more hands-on treatment in class, but for now, once you get past the limit definition, which you absolutely should know, and there always is a question about computing the limit definition of the exterior derivative, where you're doing integral by integral by integral, but once you've got that under your belt, you'll be given license to use the shortcuts. So if phi is a sum, in which the coefficients of the basis k forms are all C2 functions, that means up through their second derivative is continuous, on an open subset in Rn, then the limit as h approaches 0 exists and the exterior derivative is defined. That's the first thing. The second thing is that there is linearity. If you're taking the exterior derivative of a linear combination of k forms, that's going to be the same thing as the first relevant scalar multiple times the exterior derivative of the first form plus the second scalar multiple times the exterior derivative of the second form. Note that applied to any constant form, the exterior derivative gives 0. That's also analogous to the univariate calculus notion of the derivative. And if phi is a 0 form, i.e. a function f, the partial derivative for each individual variable multiplies d, whatever that variable happens to be. So we have d1f times dx1, d2f, dx2, d3f, dx3, and those are summed all together. And if f is a function, then if you're taking the exterior derivative of something that is already an n form, that will give you the wedge product between f, the exterior derivative of f, and the n form that you were dealing with earlier. Again, once we've tackled the limit definition of the exterior derivative, we will then be using these shortcuts very liberally, and in general, students find it pretty straightforward once they get a few examples under their belt. So looking forward to building up, assembling all the pieces on our way to understanding Stokes' theorem more fully. And of course, if you have any questions, please don't hesitate to ask.